hello, I'm Ricardo. I'm going to present the work that me and my colleagues did while at FIDSI, and it's active learning for imbalanced data under cold start. And just to give you a little bit of context, FIDSI is a fintech, and one of our main branches of business is credit card fraud detection. So it's a binary, it's in the end a binary classification problem where the imbalance between positive and negative cases is really high, and where the labels are very scarce and very hard to obtain, very expensive to obtain. And that's why an active learning solution might be, it is very interesting for us. And so what we want to accomplish with this work is to find what is the smallest sample of data that we can label in order to have high performance model that can be deployed for the first time for a given client or a given project. So, and how does active learning can help us? So imagine that you have a stream of events on a live production system, and your stream of events is being stored on a pool of unlabeled data. So imagine these are credit card transactions that are being stored on a database somewhere that don't have labels. So as time goes by, this pool of unlabeled data keeps growing and growing, and at some point it becomes very interesting for us to start labeling that data, and we want to do that as soon as possible. So one technique that you can use is active learning. So we apply an active learning policy that can be one of several, and what you want to do is to pick up an active learning policy that is going to fetch a batch of transactions from the unlabeled pool. So it will basically choose some transactions, some events from that pool of unlabeled data for an analyst, a human expert to label. And once that analyst, that human, labels those transactions as being either fraudulent or not fraudulent in our use case, we then have some labeled data, a small, it will be a small pool of labeled data, but we have some nonetheless. And with that, we can train a first iteration of our classification model that we can eventually deploy. And once we have that model, once we have labeled data, we can go back and update our active learning policy. So now we have more information, we have a model, we have some labels, and we have more data coming in from the stream of events, and we can update our active learning policy to better suit the current situation. And once we update our active learning policy, we can fetch a second batch of transactions of events to be labeled by the human analyst. The human analyst will, or the team of human analysts will label that data. Our labeled data pool will grow, and we will have, we'll have a stronger model trained with more labeled data. And we can do this for as many times as you wish. Imagine that I have a fixed number of samples that I can label. So I have a budget for reviewing transactions, and until I fulfill that budget, I can keep iterating on this cycle of active learning for as many times that it allows me. So this is why active learning is very useful for us. It is very useful for us because in our use case, labels can take time to arrive. For example, imagine that a user loses or gets his credit card stolen, and a fraudster uses that card for a while and does transactions online until the person notice on his bank balance and files a complaint against the bank, which we call the chargeback. And this may take a few days or a few weeks or even months sometimes, and that's why labels take lots of time to arrive. And it's also very useful when labeling costs is high. For example, having a human expert labeling transactions can be very costly when you have lots of labeled data to process. And it's also very useful if you have lots of unlabeled data that you can't leverage unless you use an unsupervised classification. So this is a very attractive solution for our use case of credit fraud detection at FIDSI. And with that in mind, we explore this area, and these are our three main contributions. So we are proposing an annotation strategy, so an active learning strategy that works on data sets with orders of magnitude, with high orders of class imbalancing, let's say 10 to the power of -2, -3, -4, and even higher. And that works in a cold start streaming scenario And with the cold start training scenario, what I mean is, imagine that we have a new client, a new project, or a new solution that where the client, or where there is no historical data from which to train a model with. But even in that case, we can deploy a model that starts right away collecting data and starts right away selecting the best data to be labeled, and it's able to train a high performance model very quickly from a cold start situation. And the second main contribution is an outlier-based discriminative active learning approach that we call ODAL, and it's to be used in a warm-up situation embedded in a three-stage sequence of policies. So it would be between a cold policy and a hot policy that will be a warm-up policy. And we also perform studies, empirical studies in a variety of datasets, in a variety of real-world credit fraud datasets in banking, merchants, and payment processors. And so moving on to our first main contribution, which is ODAL. So in principle, what you want to do with an outlier-based discriminative AL approach is you have a pool of unlabeled data and a pool of labeled data, and you want to create a model, or you want to somehow be able to distinguish unlabeled data from the labeled data. And what you do is you create auxiliary or an artificial label. So let's say 1 for unlabeled and 0 for labeled data, and you train a discriminative model to distinguish between these two types of data. And then you use that model to score only the unlabeled data. And let's think about this color of gradients, this gradient of colors as the scores. And what you want to do is to pick the transactions that have a higher score. So transactions that are very likely to be unlabeled. So this means that we are choosing transactions that are not very well representative on the labeled data. Otherwise, they would be scored with lower scores. So we want to pick what's in this corner, so higher scores. But this has a major disadvantage, that is, if you want to train a model in both the unlabeled data and labeled data, and if your unlabeled data is growing and growing and growing as the system is in a live production system and the stream of data doesn't stop. So as the unlabeled data grows, the complexity and the weight of training this model becomes very high. So what we are proposing is, instead of training a classifier to distinguish between unlabeled and labeled data, what we are proposing is just to train an outlier detection algorithm on the labeled data that can then be used to score the unlabeled data to find the outliers in relation to the labeled data. So would this mean that in principle we'll be selecting those instances with higher scores that are outliers to the labeled data, but that are present in unlabeled data. So this means that we will not fetch like repeated or very similar transactions from unlabeled data that already are labeled, because in principle you want to have a labeled data that is very diverse and that represents well the whole universe of unlabeled data. And this type of approach fits very well into a three-stage active learning policy, because imagine this scenario where instead of 3 stages, we only have 2 stages, which is very common in the literature to see. So in the first phase of the problem, you don't have any information at all. So your unlabeled data pool is growing and growing and growing, and you don't have any information at all to make intelligent decision on what data should be labeled or not. So you have a cold phase, and by cold we just mean that it's not very intelligent, and you don't have any label information or label data to start with. So you just fetch a random sample of data from that unlabeled data, and then you do that for as many times as you need until you find some positive cases. So until you find an example of the less prevalent class, which is very common in our use case. You can fetch data several times and not fetch a positive case due to the high class imbalance. So what happens is that you can have a long period of time where the number of fraudulent transactions that you are actually fetching to be labeled really does not rise a lot, especially in the beginning, and you can quickly move to a hot policy which is more intelligent and more sophisticated, and that will perform better. So what we are proposing is to introduce between a cold policy and the hot policy a warm-up policy, and this is where ODAL comes in, because as it does not need to know the label of an event, it does not need to know if an event is fraudulent or not. It just needs to know if there are if there is data on the labeled pool and data on the unlabeled pool. It works very on in these situations, and it will allow to switch from a cold policy to a hot policy much quicker, as it will find much quicker in the beginning more examples of the less prevalent class. As we see in the plots, what we have and what we see is that the number of positive cases that are being fetched to be labeled rises much quicker than when we're using a two stages or two-phase active learning policy, and the end and at the end, by labeling less transactions, we are able to catch more of those positive examples. And moving towards the results, so we perform several experiments on several datasets and several domains. So as I said before, banks, payment processors, and merchants, and we tested a variety of active learning strategies. And to compare those strategies against the baseline, we are comparing against an active learning strategy that assumes that we have an infinite budget to label transactions. So it assumes that every transaction or every event coming in through the event stream is eligible to be labeled, and there is an analyst available to do so. So it would be the best case scenario for that streaming scenario. And what we see when we compare two very similar policies, but at the bottom we have a two-stage active learning policy, and at the top our three-stage active learning policy with our ODAL mechanism as a warm-up policy, is that for the majority of the data sets, and here at the right we have the ranking of how these strategies perform on several time folds and on the several data sets, we notice immediately that that these strategies are rank relatively high in relation to a two-stage policy. And if we compare this type of sophisticated strategy with ODAL as a warm-up policy, we notice that comparing to a random policy where you would go to the unlabeled pool and you would fetch randomly transactions to be labeled, that the performance rises much quickly, and at the end we can reach performances that are very high and much higher than with a random policy, up to 80%. And then if we compare the results of this active learning strategy with the performance of classifiers trained with the whole data set, so where we are able to label the whole stream of events, we see that overall the ranking, so the order of performance that they appear is very similar, with the advantage that we are only labeling 2 to 10% of the total volume of transactions. And moving to future work, I'm going to just refer the most interesting that we didn't explore and we are planning to. So we would like to in the future be able to do some experiments with real analysts in a live environment. So because in this work we simulated the arrival of the labels, so we have real labels, but we are simulating the arrival of these labels to the system. And in this case, what we want to do is to somehow put the system into production and really try to see if the same conclusions hold in a live environment. Study how if it would be possible to perform some type of hyperparameter tuning and model selection for every model update, and as the active learning policy evolves over time, and also do some supervised feature selection, as the feature selection that we applied is based on the first batch of transactions, and it is unsupervised, and we don't have the labels to do that feature selection. And perhaps the two most interesting topics to explore in the future would be online model evaluation and deployment criteria. And why online model evaluation? Because if you don't have labels to evaluate your model, or if you have a very biased set of labels in your label pool to evaluate a model, how could you create a good estimate of your performance evaluation while having the system live and online? And the last would be deployment criteria. So when are you confident enough that your model is able to go to production and to be deployed? It could be things like, for example, have I reached good enough performance? How is the active learning policy evolving? And so on. And thank you. That is it. If you have any questions, please go. Okay, so going through the questions. So the question is, what model did you use to find the outliers in the unlabeled pool of examples? So you use an isolation forest. And what is the dimensionality of the examples? So by dimensionality, you mean the number of features or like the number of samples? The number of features is in the order of a couple hundred, maybe 200, 300, 400 features in some cases, maybe more. And then we use PCA to reduce the dimensions up to a point where it can explain 99% of the variance. Yeah. If you have any more questions, please go ahead. All right. I guess that's it then. Thank you.